Welcome to section 7.2, looking at two triangle theorems. Today we're going to focus on our final method on how to prove that triangles are congruent. But in order to do that, we have to know what the no-choice theorem says. And the no-choice theorem says that if you have two triangles that are congruent, or I'm sorry, two pairs of angles that are congruent in two different triangles, then the third pair of angles automatically have to be congruent. And we think about why that's true. Well, all the angles of a triangle have to add up to 180. So if the sum of the first two angles is the same, then if we're taking that away from 180, the third one's got to be the same as well. So basically, there is no choice for the measurement of the third angle. That's why it's called the no-choice theorem. So as a quick example of how we might use this in a proof, if we had here that angle M is congruent to angle T, and we're also showing that angle AM is, or sorry, line AM was parallel to line TH, what we're going to do is start our proof. And again, we want to show that angle MHA is congruent to angle TAH. So starting with the parallel lines, if I connect those with the transversal, I end up getting that Z shape, which tells me I have alternate interior angles. So it's going to be angle MAH and angle THA. And I know that's true because I just had parallel lines, which gives me alternate interior angles congruent. Mark them up. From here, I can notice in this triangle MAH and this triangle THA, I have two pairs of congruent angles. I'm trying to conclude that the third pair of angles are the same. So I'm going to conclude that angle MHA is congruent to triangle TAH. Angle. I know I said triangle, but that's the no-choice theorem. So, two pairs of angles congruent, third pair must be the same. Alright, now that gets us into angle side. Now the reason we can use this is because of the no-choice theorem, that if we have two pairs of angles, those third ones automatically have to be congruent. So we can effectively turn this into an angle side angle relationship. We're not going to do that, but we could if we needed to. So we already know four ways to prove triangles congruent: SSS, SAS, ASA, and HL. And now we're going to add our fifth. And it says if two corresponding angles and the non-included side of two triangles are congruent, then the triangles are congruent. So the side is not going to be between the two angles. It's going to be in a different location. It seems like AAS and ASA are the same thing, but they're not. So for both methods, we still need to have two angles congruent and one side congruent. The key difference is the location of that side. For angle side angle, the corresponding side that's congruent is between the congruent angles. For angle side, the side is not going to be. So now we know if we have two pairs of angles congruent and a pair of corresponding sides that match up in a particular way, then the triangles will be congruent. So we want to figure out if we can prove these triangles congruent or not. So it seems to me like we've got one pair of angles here, another pair of angles here, but the sides don't really match up to where we want them to be. One of them, this triangle on the left, looks like it's going to be an angle side angle relationship. The triangle over here on the right looks like it's going to be an angle side relationship. So can we prove them congruent? Well, no. The congruent sides are not corresponding. They're not in the same location. Here we've got another pair of angles congruent and another pair of angles congruent, and our sides seem like they match up. But if you notice the angle relationship right here, this is kind of the key. Across from this angle with the two tick marks or two arcs in it is the congruent side. If we go to the other triangle, it's not in the same spot, which tells me that this will not be angle side. It looks like it might be, but the angles don't match up in the right spot. The congruent angles are not corresponding. And for this one, we've got one angle there, one pair of angles here, and across from these angles with the two arcs is a side. Across from these with the two arcs is the side. So it seems like we've got a pair of angles, another pair of angles, and the non-included side. Those triangles would be congruent by angle side. So as an example, how does this work in a proof? Well, I'm going to mark off the given information that we have an angle O and congruent to angle E. And I have circle W. Now, anytime we have a circle, that's going to tell me that I probably need to do radii, get some radii congruent. So it looks like I only actually have one pair of radii, WP and WR. WO and WE are not radii because they don't go all the way to the edge of the circle. So I can start off and say that WP is congruent to WR, and that's because all radii of a circle are congruent. So mark that up. And the other thing I notice about this diagram is that we've got these two lines that are intersecting. So we're going to have four angles that are formed. The ones that are across from each other are those vertical angles. So I know this angle is congruent to this angle. So in my next step, I'm going to say that PWO angle is congruent to angle RWE. And that's a vertical angle theorem. Alright, well, now I have a pair of angles congruent, I have a pair of sides congruent. If you notice, the angle right here across from that is a congruent side. The angle right here across from that is the congruent side. So it seems like my triangles are congruent now. And that's our new method to prove triangles congruent. Angle, angle, side. Two angles, side not included. Now I pick out the parts. PO, RE, first and third letters, naming's good. So PO is congruent to RE. And that's because of CPCTC. Corresponding parts of congruent triangles are congruent.